Good morning to everybody. Welcome to mass transfer course. Today will be the lecture 6. So in lecture 5 we have developed generalized equation for molecular diffusion. What is this one? That is flux Na equal to Na plus Nb to Ca by C minus dAb dCa by dZ. This is the flux in terms of concentration. Then Ca equal to Pa by Rt, then it will convert at Na equal to Na plus Nb, Pa by P minus dAb by Rt dPa by dZ. And in terms of mole fraction for Ya, that is for the gas phase, that will be Na equal to Na plus Nb into Ya minus dAb P by Rt into dY A by dZ as Ya equal to Pa by P. Now as Ca equal to Xa into capital C. Therefore, this equation will convert to this equation, that is for the liquid phase, and C is average molar concentration of the solution, that will be rho by m average. Okay. These equation we developed last time. These are the generalized equations. Today we will apply these equations in various mass transfer processes. Now what are the different types of mass transfer processes? Here I have written steady state mass transfer processes in binary mixer. I use this word steady state. We know the steady state means any property at a particular point will not change with the time. Okay. Let's take in a separation equipment, in a particular location, if temperature does not change with the time, that means it is under steady state. In general, chemical plants run under steady state condition. Generally, chemical plant runs for 330 days in a year, and remaining 35 days they go for maintenance shutdown. So all the equipments, separation equipments, will run under steady state. Therefore, it is very important to design the equation under steady states, because plants will run for the steady state. Yes, you can tell initially there will be unsteady state, but initially for 1 day or 1 hour it will be unsteady, then remaining 330 days it will be steady state. So that's why design of equipments under steady state is more important, and that's why if you see in general we in chemical processes we do the calculation, most of the calculation we do under steady state condition. Here in mass transfer equipments whatever calculation we will do, it will be mostly under steady state. That means the flux Na, that will be under steady state, that will not change with time, because pressure difference between 2 points at a steady state will not change. Therefore, or concentration difference between 2 points will not change, and therefore the flux also will not be changed. And there are 3 types of mass transfer processes. First one is diffusion of A through non-diffusing B. So here we will consider only binary system. In mass transfer 1 and 2 we will discuss about only the binary system, that is A and B. Diffusion of A through non-diffusing B. What is this? I have taken the example removal of carbon dioxide from mixture of hydrogen, nitrogen and carbon dioxide. Already we discussed this example in detail, and for this separation we use ethanol. Here if you consider that carbon dioxide is A and hydrogen, nitrogen together as a single component B. Now here carbon dioxide is diffusing from gas phase to liquid phase. So it is mass transfer is going on from the mixture of A and B, where A is carbon dioxide, B is together hydrogen and nitrogen, because this is not diffusing. So carbon dioxide diffusing from gas phase to liquid phase. However, nitrogen and hydrogen is not diffusing from gas phase to liquid phase. So here carbon dioxide is diffusing and hydrogen and nitrogen together they are non-diffusing, and as hydrogen and nitrogen together we can consider here as a B. So diffusion of A through non-diffusing B. Similar thing will happen if you take removal of carbon dioxide from mixture of methane, carbon dioxide H2S, that is a natural. That is also diffusion of A through non-diffusing B. In that case carbon dioxide will be A, and methane, carbon dioxide and H2S will be A, because these two are diffusing from gas phase to liquid phase, and methane will be the. So there will be number of examples. Already we have taken number of examples. Among them, sum up will be diffusion of A through non-diffusing. Second is equimolar counter diffusion. Equimolar counter diffusion of A and B. And here I have taken the example of coal, burning of coal. Now, when we burn the coal, let's say coal is one spherical particle, where I am burning this one, then the reaction is the carbon, whatever present in this particle, spherical particle, this is reacting with the atmospheric oxygen, then it is carbon plus oxygen, it is producing carbon dioxide, then carbon dioxide is again coming to the atmosphere. So in this case, let's say this is one coal particle, and when oxygen is diffusing from air, then there will be one boundary, hydrodynamic boundary. So oxygen is coming from gas phase to this interface, and there will be one boundary layer. So here Here oxygen is A is coming in this direction. When it is reaching to the surface, then carbon is present here, carbon plus oxygen, that reaction carbon dioxide will, and then again carbon dioxide is going out from the surface to the atmosphere through this boundary layer. Now in this case, one molecule of oxygen will produce one molecule of carbon dioxide. That means how many molecules of carbon oxygen will come to the surface of the carbon particle, these and same number of molecules will go from the surface to atmosphere. That's why here if you see, this is the equimolar counter diffusion. How many moles of oxygen is coming? Same number of moles of carbon dioxide is going from the surface. So this is equimolar counter diffusion. Generally, equimolar reaction, equimolar heterogeneous reaction, catalytic reaction, these are also equimolar counter diffusion of A and B. Now, what is equimolar heterogeneous catalytic reaction? What is its mechanism? That you will study in detail in your reaction engineering course, but I am giving one simple overview of what is equimolar heterogeneous catalytic reaction. So our equimolar means, you understand this one, that the reaction is A to B, 1 mole to 1 mole. This reaction is happening in a heterogeneous catalyst. That means, let's say this is one liquid phase or gas phase AB, and catalyst is solid. And in catalyst generally that is porous. Why this is porous? If it is porous, then there will be more active sites inside the catalyst, and A will come inside this one, and these are the active sites, and A to B, that reaction will take place, then B will come. So porosity is required because to increase the surface area. Now in this reaction, let's see how many steps are happening. First one is, this is catalyst surface, and this is solid, and this thing A, this is either gas phase or liquid phase. When A is coming from gas phase or liquid phase, this one, so there will be one hydrodynamic boundary layer. That means there will be one resistance. So A from bulk to this catalyst surface, so there will be one mass transfer. So that is called external diffusion. Step 1, mass transfer of A to the surface. That is called external diffusion. When A will reach to the catalyst surface, because most of the active sites are inside this, very few are active sites are outside. Generally active site, most of the 99.9% active sites are inside the pores. So A will diffuse through the pores and it will reach to the active site. So this is called internal diffusion, that is a step 2. So step 1 is external diffusion, step 2 is internal diffusion. Now when it will reach to this active site, then A will adsorb to the catalyte active sites, that is adsorption. So external diffusion, internal diffusion, adsorption. Once it will adsorb, then the reaction will take place surface A to B, that is this is the reaction. But when B will produce, it has to come out. If it does not come out, after some time no active sites will be available, so no reaction will take place at steady state. So when B will has to come out from this active site, first that will be dissolved. B will dissolve from the surface. Right? Then after dissolution, that is step 5, then it will come to outside at the surface of the catalyst through internal diffusion. That is also internal, but it is coming out. When it will reach to the catalyst, then it will be the external diffusion. So there are 1, 2, 3, 4, 5, 6, 7 steps in heterogeneous catalytic reaction. Any heterogeneous catalytic. And in this case, the reaction is equimolar, that is called equimolar. If it is A to 2B, that will be non-equimolar, or 2A to B, then also it will be non-equimolar. But in this, among the 7 steps, you see only step 4 is reaction related to your reaction engineering. Remaining these 3 and these 6 steps are related to your mass transfer. So catalytic reaction is one classic example where you need the thorough knowledge of both mass transfer and heat transfer, and you will study this catalytic reaction engineering reaction course in CRE 2, and by that time you learn these processes. So here also now you can understand, this is also equimolar count. How many moles are coming, that much of how many reactants are coming inside the pores, this much more B products are going out. So this is also the equimolar counter diffusion. Okay. Any heterogeneous, but if reaction is equimolar, then it is called equimolar counter diffusion. Now there will be non-equimolar counter diffusion. It is same, only the thing in this case I took A to B. In this case I have taken the example of synthesis of ammonia, where 1 mole of nitrogen, 3 mole of hydrogen producing 2 mole of ammonia. It is also catalytic iron, spongy iron is the activated spongy iron is the catalyst. But here the diffusion is non-equimolar, means 4 molecules are entering, okay, and 2 molecules are coming out. But this is also counter diffusion. Okay. And if you see any transport processes, there will be thousands of examples, but it will fall under one of these categories. Either it will be diffusion of A through non-diffusion B, or it will be equimolar counter diffusion, and or it will be non-equimolar counter diffusion. Any transport processes will fall under one of these 3 categories. Now when one problem will be given to you, first you have to identify your problem is in which category. Okay, so now we will calculate the flux, mass molar flux for these 3 systems. First one is diffusion of A through non-diffusing B. So Na equal to Na plus Nb Pa by P minus dAb by RT into dPa by dZ. This is my governing equation we have derived already in terms of partial pressure. The component B being non-diffusing, if B is non-diffusing, that means Nb that will be 0. So this equation becomes Na equal to Na into Pa by capital P minus dAb RT dPa by dZ. Now if you take this side and you take the Na common, then 1 minus Pa by capital P equal to minus dAb by RT into dP by dZ, and P minus PA by P into NA equal to minus DAB RT dPA by dZ, or I can write NA into dZ, okay, minus this P will come here and dP into P minus PA. So this is my equation. Now what I will do, here I told we are calculating, we are doing this thing for steady state condition, and steady state NA is constant, flux will be constant. Now what is the flux between 2 points? Let's take at Z equal to 0, partial pressure of A equal to PA0, and X at Z equal to L after certain distance, 0.1 at 0 point and L point, okay, and then the partial pressure is PAL. Let's take. Now I will make the integration of this. At 0, the partial pressure of A, PA0, at L, that is PAL. It may be noted that PA0 will be higher than the PAL, then only A will flow from 0 point to L point. Okay, I do this. Now this is equal to NA into L, DAB P by RT, okay, and there is one minus and another minus, so it will be positive, so ln P minus PL minus this. So my equation becomes flux equal to DAB into P RT into what is the distance between 2 points, ln P minus PAL P minus PA0. Okay. So this is because I want to calculate the flux, because always that is my objective. I want to keep the flux as high as possible. That's why I have to calculate this one. Then after calculation, if I see this is not high, then I will try to increase this one. Okay. Now if you see in this equation, I am calculating this flux, but this is the equation. But if you see in mass transfer, generally what is the flux? Flux equal to driving force by resistance. Driving force means in this case it should be PA0 minus PAL. In this case the pressure difference is the driving force, PA0 minus PAL. Okay. But here you see that is not within this equation, but it can be represented like this: flux equal to driving force by resistance. Let's try to do this. Now since the where mass transfer is taking place, the total pressure is constant. I am giving you an example. Let's take, you have a separator, gas phase, okay, and outside you kept it open to atmosphere. Then what will be the pressure inside your separator? Let's assume there is no energy loss due to friction. Then that pressure within the vessel will be the 1 atmosphere. Now if A increases, then B will decrease. Partial pressure of A, if there are two components, when partial pressure of A will increase, then partial pressure of B will decrease, and when partial pressure of B will decrease, then partial pressure of A will. That's all. But total pressure will be constant. So the total pressure P equal to at 0 point, that is PA0 plus PB0, and that will be same that PAL minus PB. Now here this is higher than this, that means this is higher than this. So I can write PA minus PA0 equal to PB0 and P minus PAL equal to PBL, and I can write PA0 minus PAL equal to PBL minus PB0. So with this thing, now if I put this thing in this equation, then what I can write, Na equal to DAB into P by RT into L, that was there. Now here I am, what I am doing, I am writing PA0 minus PAL, because I know this is the driving force, that's why I am writing this one. And as I wrote in numerator, so denominator also I am writing PA0 minus P. Now ln P minus PL, P minus PL equal to PBL, and P minus PA0, P minus PA0 equal to PB0. Okay, and now if you see PA, here this part I am keeping. Now PA0 minus PL, I can write PBL minus PB0. So I am writing PA0 minus PAL, PBL minus PB0 instead of PA0 minus PL. Instead of PA0 minus PL, I am writing PBL minus PB0. And this term I am keeping down. So now what is this? This is your very similar to your log mean temperature difference, delta T1 minus delta T2 by ln delta T1 minus by delta T2. So that was the LMTD, log mean temperature difference. In this case, this is log mean partial pressure of B. See here, all are B, no A is there. So I can write this equation, Na equal to DAB into P RT to L to this, and this term I am writing as a PBM. So now that flux equal to Na equal to driving force, and this by this, that will be your resistance, or if you coefficient, then this by this. So that's why I am expressing the flux equal to driving force by resistance. And what will be the, now in this case, as this is log mean partial pressure difference, the profile of PA0, partial pressure of A and partial pressure of B will not be linear, because this equation suggests that should be non-linear, that will be in logarithm part. Okay. Now here, if you see, I am calculating flux in terms of pressure and partial pressures of A and B. So, but you know, other forms are also required, because sometimes my driving force will be, instead of partial pair, that will be mole fraction or concentration. So we need to, then accordingly we have to rearrange this equation. And this is the way we can convert this equation into other form. So our flux Na was DAB into P by RT into L, 1 by PB, PA0 minus PAL. I could keep that. Now Ya equal to what? Ya equal to Pa by P, or Pa equal to Y into P. So Pa equal to Ya into P, so Ya0 into YAL, and one P will be there, that will come here, that's why it is coming Pa square by L. And what will be PBM? So PBM will be, if you see, PBL minus PB0 divided by ln PBL by PB0. So PBL will be P, only P will multiply, it will be multiplied P into YBL minus YB0, ln YBL minus YB0, PP will be cancelled out. That's PBM equal to P into YBM. That means, so PBM will be P into YBM. So this one P will be cancelled out. So this will be your flux of A in terms of mole fraction in the gas phase. Why? The driving force is in terms of mole fraction. YA0 or 0.0 and YAL. Again, I can convert this equation in terms of CA, because CA equal to PA by RT. So this equation I can write, and PBM will be RTCBM. So PA equal to RTCA. So this equation, if I write DAB RTL, okay, RTL 1 by PBM CA0 minus CL into RT, so RT will cancel out. Then PBM equal to CBM RT, so then it will be DAB P RT into L by 1 by CBM into CA0 minus CL. So for gas phase only these three concentration are possible. Either you can express in terms of mole fraction, partial pressure, or you can express in terms of mole fraction, or you can express in terms of molar concentration. Okay. Now what is C? CA. C equal to P by RT, that is equal to C. P by RT equal to C. Okay. And CBM will be into CA0 minus CL. Because if you see, I have already expressed this in terms of concentration. DAB P RT into L 1 by CBM CA0 minus L. Now in case of liquid phase, that should I express in terms of C, that capital C equal to P by RT. That's why I am writing DAB CL, then remaining thing. Now what is, now I want to express in terms of mole fraction, then Ca equal to Xa into C. Okay, that means Xa X0, then C. So C will come here. CBM, CA0 I kept this one. Okay. Now CBM equal to CXBM, so it is coming out. Then X, then it is coming ONC. So that will be Na equal to DAB by L into C by XBM into X0 minus X. So here I am in liquid phase, I am defining the driving force in terms of concentration or liquid phase moles fraction, because I want to, that means I have learned to calculate the fluxes of A in various form. Because in problem statement I don't know in what unit, okay, it will, that driving force will be expressed. Either it can be partial pressure, or it can be molar concentration, or it can be mole fraction in gas phase, and for liquid phase either it will be mole fraction or molar concentration generally. So accordingly whatever will be the driving force, accordingly easily we can calculate the molar flux, and the calculations are simple. That these are the few things you have to remember, and then you can make it very easy. Now second thing is equimolar counter diffusion. That's mean diffusion of A through non-diffusion. Diffusion. So A is diffusing one way, B is diffusing just opposite side. And here we have taken the example of burning of coal, where oxygen is coming towards the coal particle and carbon dioxide is going from the coal particle to the atmosphere. That is equimolar counter diffusion. If it is an equimolar counter diffusion, means Na equal to minus Nb. Whatever the diffusion of A, Nb will be same but in opposite direction. So that means this term will be 0. I mean Na equal to minus dAb dP A by dz. Now integration 0 point that Pa0 at L, that is this thing, that means I got Na equal to dAb into Pa0 minus PL by RT. And here you can see when I draw the profile of partial pressure with respect to distance, it will be linear. So when the diffusion of A through non-diffusing B, the profile of partial pressure will not be linear, but in case of equimolar counter diffusion, that will be linear, because this is on a linear equation. Now how here I calculated this thing in terms of where here directly I have this driving force Pa0, so I need not to make the calculations what way I did in case of diffusion of A through non-diffusing B. Now what I have to see, what will be my flux Na in terms of other concentration. So this is my Na equal to Tab Pa0 minus Pa RTL. Now Ca equal to Pa by RT. So I can write, or then that's mean Pa equal to CRT. So Pa0 Ca0 RT, Cl RT, RT here, and this RT will cancel out, and this will be my flux in terms of molar. This will be for gas phase, and this will be for both gas phase and liquid phase. Now for mole fraction for gas phase, that is Pa equal to Ya equal to Pa by P, means Pa equal to Yap. So from this equation, if I write Pa equal to Ya into P, Ya0 into P, Yl into P, so P will come, so RT dAb RT P dAb by RT P by L. This will be flux. Here my driving force in terms of mole fraction in the gas phase. Now if this thing, if I calculate Ca equal to XA, so XA into C, and this will be my flux in terms of where driving force is mole fraction, but this is applicable for the liquid phase. So here we are calculating the flux of A, and because we know the calculation of flux is very important in designing the mass transfer equipment. If flux is high, I can get the better separation in mole separation equipment. And here we have, and we know that there are different types of concentration, accordingly there will be different types of driving force, and that's why we have calculated all the possible ways for both diffusion of A through non-diffusing B. That is one case. Another case is equimolar counter diffusion. Now third thing is non-equimolar counter diffusion. Non-equimolar counter diffusion will be similar to equimolar counter diffusion, only according the stoichiometry it will change, and it is very case specific, and we will do this one with one problem. Okay, so today we have calculated the fluxes for three cases from the governing equation of mass transfer equilibrium. What are the different cases? One is diffusion of A through non-diffusing B, diffusion, equimolar counter diffusion, and non-equimolar. So thank you for your attention, or we will stop today. Thank you.